Hello friends, welcome back. Today we are going to learn a topic sampling theorem for bandpass signals. So it's a very important topic and it is not covered many times, but we are going to see it today. Okay. So what is a bandpass signal? Bandpass signal looks like this, where the signal is present for a specific band of frequency. It's not low frequency, it's not the high frequency. It's a specific band. So here I'm drawing this axis kilohertz. So the signal is present between 1 kilohertz to 2 kilohertz. So its bandwidth V is equal to this higher frequency minus this low frequency. So it is equal to 1 kilohertz. Okay. So this is a band pass signal and we should obviously apply some different rule for sampling this. So why it is required, let us see that. Okay. But before that, we'll write the formula that we derived for in sampling theorem for low pass signals. So the same formula we are going to apply, but we will see what modifications can be done there. Okay. So actually we are not modifying the formula, but we are seeking for some changes for the betterment. Okay. So x del of omega, it is the sampled signal. So it is equal to 1 upon Ts. It is the separation factor. Ts is the sampling interval, summation n varying from minus infinity to infinity, x of omega minus n omega s. So what it represents? Omega minus n omega s. These are various images of the original spectrum. X of omega is the original spectrum. So I can write this like 1 upon Ts, like it's the sum of, like, say x of omega plus x of omega minus omega s plus x of omega minus twice the sampling frequency and plus so on. And on this side we can write x of omega plus omega s. So it's the original spectrum and these are the shifted versions on right and left hand side. Okay. So just we want that this spectrum should not, original spectrum and images must not clash with each other like this. If we select a sampling frequency which is double of that, so it's the double, let us say omega s is twice omega h. So it is the cut to cut sampling. So images and the original spectrum is not clashing, and here it is not mixing with each other. And if we select a sampling frequency which is lower than this original omega s, twice less than this value, suppose this value, then what happens? This mix here. So aliasing occurs at this point and we don't want that because we cannot recover our signal. Okay, here the mixing occurs. So the signal looks like this and we cannot recover the original signal back from the spectrum. Okay, so we don't want these images and the original spectrum mix with each other. Okay, so let us apply this definition to this. Let us see what happens. So I'll draw the axis first. So it's minus 1, 1, 0, 9. Okay. So let us draw our original. So it is suppressed. I'm not drawing the separation factor here. Okay. So it's the original. And now we'll draw the images. Okay. So this is the x of omega. So I'll write here x of omega. Now x of omega minus omega s. So it's 2 kilohertz, which is the higher value. So omega s is equal to 4 kilohertz. Okay, 4 kilohertz. So here, now we'll draw okay. So this is what? X of omega minus omega s. Okay. Now we'll draw on this side. Now minus 4 kilohertz is here. So we can draw like this. So this is x of omega plus omega s. Now we can see there are a lot of gaps. Okay. Then there is a question, can we utilize these gaps? Because there are gaps and we can utilize this bandwidth for the images. Okay. And can we select a sampling frequency which might be lower than this defined sampling frequency? Can we do this? Okay. So let us check one way. Okay. So if it is the original spectrum, can we somehow shift the signal, okay, like this? Okay. Can we do this? Okay. Can we again shift the signal like this? Okay. So we are shifting by this small factors. Okay. Not by 4 kilohertz. Okay. So we are shifting by some less sampling frequency, and still these are not mixing with each other. So it is going in a correct way. So we can do that. We can sample the bandpass signal with some lower sampling frequency which is defined by the original sampling theorem. Okay. So there are two conditions which we need to check for a bandpass signal. We'll check that conditions first, and then we'll see with how much frequency we can sample the signal which is lower than this 4 kilohertz, means twice the higher frequency contained in the signal. Okay, so let us check. For the two conditions, I'll write here. First of all, we need to find FC, that is the center frequency, which is equal to the mean of these two values. So omega h plus omega s divided by 2. So this, in this case, it is 3 by 2, that is 1.5 kilohertz. Okay. Bandwidth is 1 kilohertz. So FC must be greater than this bandwidth by 2. Let us check if it is true. 1.5 greater than this 0.5. B by 2 is 0.5. So it's greater than, so this condition is fulfilled. So bandwidth and higher frequency relationship. Let us check. Bandwidth relationship with the higher frequency omega h. Integer multiple. We want to check that omega h is integer multiple of the bandwidth. Okay. So it is 1 and the higher frequency is 2 kilohertz. So we can see that it is integer multiple of the bandwidth. So we can apply the sampling frequency which is lower. So let us see what is that new sampling frequency value. So that new frequency value can be equal to twice the bandwidth. So this is our new formula. So with this, let us check what happens in the spectrum. We want to check if aliasing is occurring or not occurring with this. Twice the bandwidth. So twice the bandwidth, a new frequency would be equal to twice the bandwidth is 1, so it is 2 kilohertz. So let us check with omega s is equal to 2 kilohertz. Okay, I'll draw the axis first. One, two, three, four, 5, 6, 7, 8, 9, and in this in kilohertz. Minus 1. Okay. So this is your sampled version. So let us draw the original one. So this is the original one. I'll name it x of omega. So let us draw the shifted version, or call it images. So first shift by omega minus omega s, that is omega minus 2 kilohertz. So let us move this point 1, 2. This point by 2, 1, 2. So this is x of omega minus omega s. Okay. Now omega minus 2 omega s means omega minus 4 kilohertz. So let us move this point, okay, this point by 4. 1, 2, 3, 4. So this will be like this. Now this point 1, 2, 3, 4. Okay, so it will be like this. So this red is x of omega minus 2 omega s. Okay, now let us move on this side. Okay, let us check. So I'll draw in red. Now omega plus omega s, omega plus 2 kilohertz. Let us move 1, 2. So it will be like this, and this by 2, 1, 2. Okay. So this is x of omega plus omega s. So we can observe at this point, if we go on drawing the images like this, we can complete like this. See. Okay. So we can complete this spectrum, and where we are able to see here that there is no crossing between the original spectrum and the images. So it is possible to sample with the sampling frequency which is lower than the sampling frequency which is defined originally by the sampling theorem, that is, it is double of the higher frequency. So in case of bandpass signal, because of this gap, it is possible to sample with lower sampling frequency. We are always aiming to get lower and lower sampling frequency. We don't want to go for higher and higher, because it is costly to use higher sampling frequencies. So we want to get to lower sampling frequency, and it is just possible in bandpass signals where these two conditions must be followed, that the center frequency must be greater than the bandwidth by 2, and the second condition is the bandwidth of the bandpass signal, okay, and the relationship between bandwidth and the higher frequency. The higher frequency must be the integer multiple of the bandwidth. Then and then only you can sample your signal, bandpass signal, with twice the bandwidth of the signal. Okay, so this is for today. In the next lecture, we'll see if this bandwidth and higher frequency relationship is not being followed, then what we can do. Okay, is there some other criteria to do that? Okay, so we'll check that in the new video. Thank you.